Hello and welcome to a presentation I've entitled Solving Differential Equations Using Power Series Expansion. In this presentation, I'm going to discuss with you a solved example, which is a first order differential equation, which is solved using this power series expansion. First of all, I'm going to solve the equation using the integration factor, and I show you also the solution using the method for undetermined coefficients. At the end, I would like you to sort of convince yourself that the solution we get as a power series expansion is actually equivalent to the solution we get when you're using integration factor or the method of undetermined coefficient. So the problem is as follows. We are to solve an equation, first order equation dy dt minus y equal to 0, given that y at 0 is equal to 2. In this case, this is an initial value problem. So in order to solve this equation using power series expansion, we have to hold on an assumption that the solution which satisfies this equation actually has got a power series expansion. But before we get there, let's look at how we can use the integration factor to solve this problem. So using the integration factor to solve this problem, we know that we have y of t as the unknown, and p of t is equals to minus 1, and the q of t is equal to 0, which is the right hand side of the equation. So then, as you can see now, if we are going to use the integration factor, we then need to find the integration factor. So computing the integration factor, we get that the integration factor is simply e to the power minus t. By integrating p here, we get that. And then what follows is what we know, which is that the unknowns, the solution, is given by this integral equation. I'm saying integral equation to emphasize that this equation which given involves integration. But fortunately, we can see that under integral sign, we actually get a 0, which then turns out that the integral of such is equals to c. And then that leads us to concluding that y of t is simply c multiplied by e to the power t, just making a y subject formula in this equation. Say y of t multiplied by f t equal to c. And then after that, we need then to determine the unique solution given the general solution, which is y of t here. And when we determine the particular solution now, we need to consider that y at 0 is equal to 2, which actually simply implies that c is equals to 2. And then we get our unique solution as y of t equals to 2 times e to the power t. So that is the unique solution using this method of first order linear equation via the integration factor. Then moving forward, I'm not going to go through this method, but this solution, but this is what we would see if we were to use the undetermined coefficients. We still arrive at the same solution. Now we proceed to find the power series solution to this differential equation. So this is the problem given, the initial value problem, as we've seen before. And then, like we said, when we use power series solution, we first of all, we could suppose that the solution has got a power series expansion, which is written this way, c0 plus c1t plus c2t squared plus c3t squared, and so on, which we can write in a compact way using a single summation sign in this way. And then at this point, we should also note that we already have got one coefficient which we need for this power series expansion, which is c0. Like we had seen before, that c0 is actually the value of the function at 0, and then this is 2. So for this expansion, we already get c0. And then now computing the derivative of the solution, which is y of t, now it means computing the derivative of this expansion, power series expansion. And then we should note that here, to find the derivative of this, we basically need to differentiate this term by term. Like, for example, if we differentiate the first term here, we're going to get 0. Now, this is what we get. We then start the power series starts at c1, and we can write it in a compact way this way using the summation sign. I hope you can see that in every term, like we've seen here, we've applied what we call power rule. Now, we just put n down and reduce the power of t by 1, which is actually our usual power rule. Then what we've done there, I'm just emphasizing there, we've done what we call term by term differentiation. And now substituting in the differential equation, which is this dy dt minus y equal to 0, we now substitute this way, in this case now, we are only using the compact form of the solution using the summation sign. This is the first derivative and this is the solution. This is the solution, so we're subtracting or getting that equal to 0, like the differential equation states. And then in this equation, the problem which we must note before we can proceed is that the power of t here is n, and the power of t there is n minus 1, and that makes it difficult for us to continue. So to continue here, we need basically to have the power of t in the two summations being the same, and that we can do by adjusting n here. And the other problem, you can see that n here starts at 1 and there starts at 0, and so we need to harmonize this by having the two summations starting at 0 and also the power of t being a single power of t like n, which is which one actually we get in the power series expansion. So for that, we do the following adjustment. We simply replace n here by n plus 1. Everywhere there's an n in summation sign here, we replace by n plus 1, and there cn will become cn plus 1, and then this n becomes n plus 1. And as you can see, when we simplify here, we actually get power n. And here, when we do make n a subject formula, you get that n is equal to 0. By that, I'm trying to harmonize especially the power of t in the two summations and making sure that the two summations start at the same point, which is 0. And then now, once we've simplified, we've got the same power here and there. Please note that here the power of t is n, because plus 1 minus 1 is 0, so we've got t to power n here. Then we can group this and take out a common factor t to power n, and you'll see that the coefficients, which are n plus 1 times c plus 1 minus cn, we can put in bracket like this, and then the equation is still equal to 0. That we are doing just to get a single summation sign. And now expressing this as using a single summation sign actually takes us to the fact that this coefficient in bracket here is equal to 0. Why? Because if the whole summation is equal to 0, there's nothing else. T is a variable, so it takes different values of real values of t. So the only term which can be 0 here is that all these coefficients are equal to 0. Then that lands at this equation, which I number here star exclamation mark, just to mark it because I'm going to refer to it. So now having this equal to 0, I think what you can see we can do here, we can now make c plus 1 substitute formula by dividing by, first of all, adding on both sides cn, and then dividing both sides by n plus 1. We get c sub n plus 1 equals to cn over n plus 1. That is making cn plus 1 substitute formula in this very. And at this point, I think you can see that we're at a point where we've got an expression that if we had cn, we know how to get the next coefficient, which is cn plus 1, using this formula. And then we recall that in the power series expansion, the nth coefficient cn was always equal to the nth differential coefficient evaluated to 0 divided by n factorial. So that's what we know. So now if we now substitute this cn by this expression, note that here we've got the denominator n plus 1. So we're going to substitute cn here, then we get y, the nth order derivative differential coefficient of y evaluated 0 divided by n factorial multiplied by this n, which actually this way, what we're defining here, we're actually defining n plus 1 factorial, because from here we've got n plus 1 minus 1, it will be n, then that will result in n plus 1 factorial. And so we note that here that the nth order differential coefficient evaluated at 0 is equal to the n plus 1 order differential coefficient. That's what you can conclude from here, because this one is actually equals to cn plus 1. But in cn plus 1, the coefficient, we must expect here the n plus 1 order differential coefficient, which is this. So we note that. That's important to know. Then moving forward, then we can now consider n running from 0, 1, 2, 3 up to infinity in this sequence here. So in other words, we can now start from 0, substituting in this sequence here, and then get to the coefficients for our power series expansion. This is what happens. If we now put 0 here, just check, if we put 0 here, we're going to be left with C1, which we're getting there. And in the numerator, put 0, we're going to have C0. And then here it will be over 1, which you can actually take as 1 factorial, because now in C1, we would have the first order derivative divided by 1 factorial. And then moving forward, taking n equals to 1, here you will have 1 plus 1, which will give us C2. In this case here, in the numerator, it will be C1, and then we get an expression like this. But then we note that C1 is this, and when you substitute, we get C2, and you can see it here, not here, C2 is over 1 times 2, which is 2 factorial. This far, we're actually in agreement with what we know about our power series expansion. Here is 1 factorial, then 2 factorial. Then let's go to the next coefficient where n is equals to 2. We then have C3, and in the numerator, if we put 2 here, we got C3, and then we've got 2 here in the n over n plus 1, and then we take that C2, substitute here. You can see what we get here. We get 3 factorial. And then taking now n equals to 3, that's where we're going to stop. Then you get C4, which is equal to C3 over 4. And again, if we take this C3, which is here, you see that we get C0 over 4 factorial. As you can see, we've managed to express all the coefficients in terms of C0, 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 and C0 here. And you must remember that C0 is actually known is y at 0, and it was given as 2. Then now finding the general term for the coefficient, it is clear that this is going to be C0 over n factorial. Like you can see, C4 is C0 over 4 factorial, C3 is C0 over 3 factorial. So for any n in a natural number, we're going to have this as C0 over n factorial. But we know that C0 is 2, then we're saying Cn is equal to 2 to the 2 over n factorial, since we know that y at 0 is equal to C0 is equal to 2. So at this point, we are ready to give our power series, the power series expansion of our solution. In this case, we need to write that as, therefore y is equals to 2 over n factorial. Remember, this is our Cn, multiplied by t to the power n, starting from 0 to infinity. And I can simplify this further, because you can see that this 2 is actually a common factor in all the coefficients. Then we can draw it outside the summation sign. Then this will look like this. And now at this point, we've actually got the power series solution to our given differential equation. So what I leave to you to do is to convince yourself that the solutions we saw above using the integration factor and using the method of anti-term coefficient is actually equivalent to this. And that will be easy if you actually seriously looked at the homework which I asked you to do to develop power series expansion for simple functions like sine, cosine, and so on. And then moving forward, I would encourage you to try to repeat this approach to solve this problem. We're given initial value problem, which is d2 dy dt squared plus y is equal to 0, and you are told that y at 0 is equal to 0, but the first derivative is 0 is equals to 1. So what I would like you to do here is to determine the power series solution up to the general term, like we saw there in my previous version. I expressed the power series solution in terms of the general term, which was Cn, and then you must also, from your solution you get in 1, you must also try to give the elementary function represented by the expansion which you have obtained. In other words, by elementary function, I just mean the known functions like cosine, exponential function, or sine, or whatever. You must figure out what kind of function a function is represented by the power series solution you have got. Otherwise, at this point, I think I've put the method very clear. The only thing what you have to do, you've got to look at it, relook at it again in order to understand, go through it slowly and make sure that you understand and you can actually do the procedure with any similar problem you have been given. So I would actually invite you, first of all, to be able to repeat the solution I give you, the power series expansion solution, before you can attempt your homework. If you can repeat it and produce it without really looking at my presentation, then you'll be convinced that you have got the procedure. Now you can attempt this homework problem and any other similar problem you get in your test. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Wasfani Msip.